Hi, I'm Rich with insideHPC. We're here at the GPU Technology Conference in San Jose, and I'm here with Rob Farber. Rob is an industry analyst. How you doing today, Rob?
I'm doing very well, Rich. And hey, by the way, I just wanted to say I saw that Inside Media just acquired the Exascale report.
Yes.
I'm glad to hear that you're continuing to grow and prosper in many different ways, Rich. You deserve it.
Well, thank you for that. This is exciting stuff, and Exascale as a problem is not going away anytime soon, so there's plenty to write about.
Job security for me?
Yeah. Well, on to more immediate things. We're here at GTC.
Yes.
And last year we did some kind of analysis of the Jetson keynote, right? The opening keynote for the GPUs. And you made some predictions about where the industry was going. I thought we'd start there. What did you predict, and how did you do so far?
Oh, I love it. You see, being a scientist in background, I love to have my predictions validated and verified, and occasionally, every once in a while, I even get to say I'm right. Last year, what I was predicting is we're going to see the growth of GPUs from the Gemini, the twins combinations, going out to more and more GPUs utilized inside essentially a single packaging. Okay, and to enable that, we're seeing the next step right now with the NVLink. Okay, the second prediction I had is that the hybrid memory cubes, the stackable memory chips, are very important, and they're going to change the industry because you're going to have extraordinary bandwidth and you're going to have big increases in the capacity of the GPUs. Okay. Well, Jensen, happily, I seem to have been in alignment with his thinking, because we're seeing NVLink, which is basically like an interface to memory, directly to memory for the GPU. So it's a faster way to move data on and off the GPU and essentially just have a direct memory access capability. Plus we see the advent of the stackable memory chips, which we'll get into a second. But let's first drill down on NVLink, which I think is very interesting.
Oh yeah. So NVLink is it's a point-to-point connection, the way I understand it, right? And high bandwidth, but it does so in a power efficient way.
Now, it's low latency.
Okay,
it's like accessing DRAM.
Okay, so this is fast. It's coming in 2016 with the Pascal GPU in that time frame.
That's what they're saying right now. Okay, we will see. Okay,
so tell me more about NVLink. What is the technology underneath this? Is it InfiniBand? Is it like PCIe?
It's an Nvidia standard that they're creating. Now they're submitting it to a standards body because nothing like it exists right now. Okay. So I really enjoyed Jensen's keynote for many different aspects. I mean, it's the NVIDIA Wonderland, and they're addressing all different market niches, and there's something juicy and wonderful in each different market niche. But with this, when I heard Jensen's keynote, I was thinking, well, this is great. I can plug in my GPUs, and then I can take my magic NVLink connector, and I can connect them all together, and I can have all sorts of high bandwidth data goodness amongst my GPUs. Okay, that's kind of the argument that you're going to have instead of the twins. You'll have the triples and the quads or the eights or whatever. The missing link in NVLink is how you get from the GPU to the host memory, and Jensen really didn't go into that much in the talk. Happily, I caught up with him earlier this morning and was talking with him and trying to understand a little bit more about the missing link. And what you need is you have to have the NVLink on the silicon of the processing element of the processor. So he said that there's going to be power coming down the line. There's going to be ARM coming down the line. There's some issues that are not necessarily technological with x86.
Well, so a lot of platforms potentially, so the GPU could talk to the CPU or whatever that might be.
Absolutely. So you will have a high-speed, low-latency link between the host and the GPUs, solving a lot of the problems that people have been talking about. Now, I'll make my own observation here, and we will see if this pans out. And this is kind of my prediction for the future. It's speculation. This is not NVIDIA or anybody else. It's my speculation. But if you look at the NVLink connector, it looks an awful lot like a DRAM connector. And my guess is that for something that actually doesn't have the interface on the chip, there might be a DRAM interface that NVIDIA clicks into, and I bet there's going to be some sharp startup that's going to go and say, we're going to do this, plugs into the DRAM, and suddenly I get my dream, which is that you're going to have the GPUs holding all the memory and the processing compute, and the processor, the serial processor, will be stealing memory bandwidth from the GPUs. So there's no data movement. You do your massively parallel computation on the GPUs. When you need to, according to Amdahl's law, you can't do anything more in parallel. You have to do something sequentially. Then the CPU gets to steal the memory cycles. Beautiful instantiation of the hardware for an Amdahl's law machine, which is where I see GPU computing going.
Okay. So, because after all, a GPU is really just a vector processor, isn't it?
It's more than that, because it's not just vectors. You've got thread level parallelism, so you can do anything in the threads. In fact, if you catch my GTC talk, I actually show where you can take an individual thread of execution on the host processor, and I can have a bunch of those. So let's say like 15, one per streaming multiprocessor on the GPU, like a K40. And essentially, I'm treating that single processing element on the GPU, it's called an SMX processor, as a core in a multi-core processor. And it breaks the myth that we had someone walk in front of the camera. It breaks the myth that the GPUs are only good for big computational problems. Instead, what I can do is I can map lots of little small problems to each individual SMX, and actually this is going to be in production at Cold Spring Harbor. It's really beautiful how it works.
Okay, so but you don't have to wait for some future hardware.
No, this is now.
Possible. Okay.
Just took a little while to get around to actually writing the code and find the right project to use it, and it's really cool. It's fun.
Okay, so back to Jensen's thing now, NVLink, and there was also a development platform. What was that?
So Jetson?
I like Jetson TK1.
Yeah, well, so we've been hearing about the K1 processor and the extraordinary power efficiency of this. I mean, the quoted rate on the K1 is 360 gigaflops on a mobile chip, on a mobile Tegra chip. It's a complete ARM Kepler GPU combination. And at least I believe it's Kepler. And so that runs in your mobile phones, like this one. So you can have a super phone, but it can deliver 360 gigaflops, and the chip is rated for less than 5 watts, I think it is. So 360 gigaflops in less than 5 watts, running, doing your games. We saw demonstrations of a car that was driving itself using one of the K1 processors. So if you think about it, that's kind of like that individual core on the GPU that I was talking about. It's just a single one, so you can assign one per task. So I can see for HPC, and since this is inside HPC, the Barcelona Supercomputer Center kind of led with the ARM GPU supercomputer system. Well, let's just say that it's 5 watts for 360 gigaflops. That means that you can have a tens of teraflop device that will plug into your PCI slot, and we're going to see a tremendous boost in the power performance ratio. So really extraordinary numbers of flops per watt.
So as a development platform for under $200, 192, which has something to do with the cores, I think.
There's 192 CUDA processing cores until marketing got a little carried away.
So it's kind of like the Raspberry Pi thing. All the ports, everything you need there is to develop for, right?
If Nvidia doesn't do this, there's going to be Raspberry Pi or somebody's going to do it. That's going to be like the most awesome little hobbyist development platform, and it fits entirely in with the Nvidia philosophy that what Nvidia does is they sell the product to their customers, who are actually the guys who develop the products that sell to the end consumer. If you think about it, you take the K1, stick it on a system on a chip with a little bit of associated hardware on that. So you have
and this thing boots Linux, by the way.
It boots and runs
Ubuntu's right on this thing. Right.
And then you have your little interface. And shrink it down now to the actual size of the K1, and you're going to have a little tiny, basically micro SCSI Linux supercomputer that can do 360 gigaflops per second. What can you do with that, guys?
Well,
supercomputing for the masses at low power on a battery.
Okay. So that's exciting. What else was in there for the HPC crowd? There was a lot of talk of machine learning and things like that. Something that I don't remember hearing about last year.
Well, if you went to my GTC presentations, excuse me very much, Rich.
Your stuff's just way over my head.
Well, in which case I'm not teaching it right. Well, in fact, I actually taught this machine learning at the international school and on a recent trip to Saudi Arabia, where we had kids from all over the place. And the way I introduced machine learning was, we know that in Star Wars, the young Darth Vader builds 3CPO, the walking, talking, human cyborg relations robot, from junk parts. Okay?
Yeah.
So the view of the future is, at some point, it's going to be child's play to build a walking, talking, thinking robot. So in my GTC presentation last year, I showed how to teach a network to read aloud, which, you know, the kids love 3CPO.
Sure.
They kind of went, wow, it's reading aloud. It took me a long time to read aloud. But then I showed them Google Translate, where since this is a multilingual crowd, I was able to put in, you know, hi there, my name is Rob, and other messages into Google Translate, and it would pronounce what I wrote into the screen in their particular language, which I don't speak. Well, if you think about it, that's just going from looking up the right words to reading aloud in the different language. So the kids were able to make the link that, yeah, you can use machine learning to do something complicated like learn to read aloud. And this is how commercial companies like Google are doing things like translating in basically real time from text to speech. They loved it, and they ate it up.
So why GPUs for machine learning? Where's the connection?
Oh, I'm glad you asked that. You see, so those nice little GPUs that you plug into the PCI bus, well, with those, I'm actually able to show that you get 700 to 800 gigaflops of average sustained performance out of a single GPU on a generic machine learning problem, like learning to read aloud, or for big data problems like principal components analysis, commonly used by everybody in analytics, or nonlinear principal components analysis. Not only do you see that close to teraflop performance, but you see that the performance increases on the nonlinear problems, which is great because as scientists, we're trying to solve problems that are not linear but nonlinear, because the real world is nonlinear.
Sure.
Now, what happens when it becomes too big a problem for one GPU in your box? Well, you add more GPUs in your box. What happens when it becomes too big for a box? Well, with that same teaching code that I presented last year, that obviously you slept through my talk, is that you can scale to the world's largest leadership class supercomputers. And the straight line that I drew with my fingers, it shows that on the Oak Ridge Titan supercomputer, thank you very much to Oak Ridge for letting me run on their system, on 16,000 GPUs I achieved 13 petaflops of average sustained performance. Average sustained, that's including all overhead for communications, all jitter as the machine is running for a long period of time, so network congestion and everything. That's average sustained performance, which bodes extremely well for very, very large problems. In fact, using OpenACC, if I may do a plug for my OpenACC book, we will be showing that you can achieve hopefully 20 petaflops using OpenACC running on the GPU as well as on the host processors all at the same time.
So is that your next project then?
That's one of my next projects.
One of your next projects.
I'm having so much fun. I get to be a vagabond traveler, flying around, teaching around the world. So if you need a class in GPU programming or comparisons, look me up, and I'm on the web. You can reach me through the website. I'm very happy to teach this technology and teach you how to achieve it very well.
Well,
good performance.
You just came off a class. What did you teach this week? What were you doing? Was it machine learning again, or what were you teaching? Was that yesterday?
The class that I taught was my presentation this morning.
Oh, okay. I got it. All right, well, I'll cut that out. All right. So,
I mean, I could talk about Saudi Arabia, but or France or other places.
All right. So what haven't we covered before?
So what we really haven't covered is the stackable memory chips. So why is that important?
That's just the So all right. So Rob, we haven't talked much about the stackable memory because this is basically just hybrid memory cube that everybody's going to have access to, isn't it? I mean, this is an industry standard coming around the pike from Micron.
Yes and no.
Such, right?
Yes and no.
Yes and no?
Well, yes and no. So we all need more memory. We all need more memory bandwidth. And given that with a hybrid memory cube, you can get a terabyte of sustained performance from each cube.
Okay.
So the 6 memory channels on your current GPU, you could have a 6 terabyte average sustained performance. That's about the performance of the register file. I mean, it's lovely. Okay. So you get that in an actually power efficient fashion, and you can get GPUs, since they're stacking the memory, with 5 to 6 times the memory capacity of the current set of GPUs. What's very interesting in my mind about Jensen's presentation is they were showing their own Nvidia stacked memory modules on there instead of the industry standard consortium. If I can tell a very quick story, at one of the first GTCs, I was talking with Jensen, and he said, why did we spend $1 billion developing CUDA when we could have ran with OpenCL? And part of the idea behind that is that OpenCL is a standard-based bodies. It wasn't going to move as quickly as he wanted it to. More than that is there's enough friction inside the OpenCL standards committee where OpenCL actually messed with the business plan of some of the partners, so that even delayed things a bit more. So he just decided to do an end run around and just develop CUDA. He spent $1 billion in the process of doing it, but look what he achieved.
Yeah,
okay, so the proof is in the pudding. We'd see CUDA now pretty much everywhere.
Yeah.
I'm seeing a similar end run behavior by Jensen around perhaps the Hybrid Memory Cube consortium by doing their own stacked memory interface and doing their own internal NVIDIA version, which may become a standard in the future, but at least we'll get it to market sooner because you can see the pressure that NVIDIA and the other computer manufacturers are on to deliver this higher memory performance and this higher memory capacity. Because big data, inside big data, we all know how important that is. And with scientific computation, we're all getting into big data anyways. So the whole idea is to bring the product to market much, much quicker and then go to the standards body. So I'm very excited about the possibilities
well,
of that.
I was impressed that they are going straight for the bottleneck problems because, you know, from day one it's like, well, you got to move that data across that PCIe bus, and that's just going to only go so fast.
Yep.
And it's not going to take you to exascale in places like that.
And NVLink is supposedly the solution to that problem because you'll have DRAM speed and access.
All right.
So it's a fun world we're in, Rich. Wonderful technology developments.
It is, and you know, I appreciate your insight. So, any other predictions for us today? So I'm going to pin them on the board next time and track you down.
Please do. But I think K1, once it's out in volume, is going to revolutionize gaming. It's going to revolutionize the embedded system market. It's going to start introducing robotics. If we saw a car drive out on stage and at GTC this year powered by that K1 module, think of all the different other applications that we're going to see being applied to that. In vision recognition, augmented reality games, I think there's going to be a gold rush of augmented reality games for the new platforms. By the way, those who attended GTC this year, they got a free Nvidia Shield, which I think was brilliant because it gets everybody thinking about what they can do for changing that game console with a K1.
Yeah, that was quite the surprise at the end. You know, that one last thing, the Steve Jobs thing is, we're going to give you one.
Yeah.
Everyone gets one of these. I'm like, that's one. I don't think Steve ever did that particular trick. So good for Jensen there.
Yeah.
Well, Robert, I appreciate your insight. Thanks for coming on today.
Thanks, and I look forward to talking to you next year and see if I'm right once or twice in my predictions. We'll see. Thank you much.
You bet. Good job.